Hello, everyone, and good morning. My name is Beth Capellas, and I'm the Sales and Support Manager here at Triangle Microworks. I would like to welcome everyone to our latest webinar, Charting a Course to a Digital Substation, How to Integrate IEC 61850 in Your Existing Solutions. This is a three-part series. Part 1 and Part 2 have already been held, and recordings can be found at our website, trianglemicroworks.com. I see a lot of familiar names on the attendee list, so I appreciate everyone that's been with us for the whole series, and welcome back to Part 3. For anyone that is new and this is their first time joining this part of the series, you do not have to have watched Part 1 and Part 2 to participate and understand Part 3. They are related, but they can stand on their own. In today's webinar, we'll be focused on strategies for integration of DNP3 and IEC 61850. So for all the new folks that have joined us today, I would like to go over some housekeeping items while everyone is still joining. The webinar is scheduled to be 1 hour long. We have quite a bit of material to cover, so we are going to try to take at least 2 breaks to answer questions. The audience is on mute, so go ahead and submit your questions online using the webinar toolbar under the section titled Questions. You can submit your questions as soon as you have them. Please don't wait until the end. We will begin answering questions online, as we do have several engineers monitoring the questions and responding to them directly. And we're also happy to stay on the webinar afterwards and answer as many questions as we can. So with that, I'd like to go ahead and introduce the folks behind the scenes answering those questions. Today we have with us Jim Coates, President of Triangle Microworks. We have Greg Godleski, Engineering Manager, Triangle Microworks, and Dave Galkinauer. He's our lead developer for DTM, which is one of the tools that you'll be seeing here today. Next, I'd like to introduce our speakers. We have Christoph Brunner, President of IT for Power. Christoph is a well-known utility industry professional and 61850 expert with over 30 years of industry experience. Christoph's been involved in the development of the standard since the beginning. He's the convener of Working Group 10 and member of Working Group 17, 18, and 19 of IEC TC 57. He's also an IEEE fellow and a member of several IEEE working groups, as well as a member of PSRC Main Committee and the Subcommittee H. Next, we have Jackson Moore, Application Engineer here at Triangle Microworks. Jackson received Bachelor's of Science degrees in both electrical engineering and computer engineering from North Carolina State University and has a background in power system engineering. Prior to joining Triangle Microworks, Jackson spent 5 years as a microgrid system engineer, where he designed and developed load management control systems for multi-source microgrids ranging from 1 megawatt to 30 megawatts. In his current role of application engineer, Jackson serves as a bridge between our customer and our development team, seeking to understand and solve unique and complex challenges for our clients. So now I'm just going to spend a couple of minutes telling you about Triangle Microworks and giving you some background. We were established back in 1994 and have over 28 years of communication protocol experience. We are headquartered in Raleigh, North Carolina, and have customers in over 70 countries. We work mostly with equipment manufacturers, electric utilities, and system integrators. The products we offer all support the standard SCADA protocols and fall into 3 categories. First category is source code libraries. We license source code directly to manufacturers for use in their devices and systems. This allows for a much faster time to market and greatly reduces their cost and development time. Licensing a source code library also includes support for your implementation and any issues that may arise in the field. We also provide testing tools supporting these libraries and protocols. These tools are used for communication testing in the lab or the field. They're designed to troubleshoot, simulate, and automate testing for both a single device or a complete substation. Lastly, we also provide a SCADA data gateway supported on both Linux and Windows for protocol translation and data concentration with standard SCADA protocols as well as OPC. It's also available as software only or pre-installed on hardware. We are heavily involved in the standard committees that support SCADA protocols like UCA Group for 61850 and DNP user and technical committees. Through our participation, we help define the protocols, we stay up to date on the changes taking place, and ultimately provide feedback based on our customer needs as the protocol continues to evolve. So with that, I'd like to go ahead and hand it over to Christoph, who's going to kick off the webinar.
Thank you, Beth. And welcome everybody from my side to this webinar. Today, we will talk about 3 use cases where we can combine DNP3 and IEC 61850. And we are starting with a quite straightforward use case. That's when you have basically a DNP3 based substation and we add IEC 61850 to this substation. So the use case looks like it is shown here. We have our relays in the system. The relays have a DNP3 communication as an outstation to our gateway. The gateway has on one side DNP3 for the local substation, our Ethernet, and we also talk DNP3 towards the control center. However, what we would like to achieve is to reduce the wires that we have for application between the relays. So now we also add GOOSE messaging capability to our devices. So the devices will have GOOSE publishers and GOOSE subscribers. Through that webinar, we will look at this use case in different examples. So the use case where we have a protection device somewhere that initiates a trip, and in a conventional approach, you would have binary output, which has the trip signal that goes to trip the breaker, but this signal would also be routed maybe on the binary input of a device that implements the breaker failure function. And in case the breaker failure function has to operate because the breaker failed, it will send again over a wire the external trip to the devices of the neighbor breakers that need to be tripped in the case of the failure of the original breaker. So again, in a conventional approach, that will be a wire going on binary inputs on all the other devices that interface to these breakers. So as we discussed, the first approach to start using IEC 61850 would be to get rid of this wiring and apply instead the GOOSE communication service. As both GOOSE is using Ethernet and DNP3 can be run over the Ethernet, we don't need to have additional communication network infrastructure. We just can use the Ethernet network that we already apply for our DNP3 communication. So what you will see then is kind of GOOSE messages coming from these devices sent over the wire with the information, with binary information that represents this trip and external operate signal. To design such a system, we have basically 2 approaches that we can apply. The first approach, what I would call a bottom-up approach, would be that we simply configure in the IED tools, with the IED tools for these devices that are able to speak both DNP3 as well as 61850, that we configure their GOOSE messages. We more or less map the IO points that we had before on our binary outputs and inputs on GGIO logical nodes, create data sets, a GOOSE message with GGIO, and on the subscriber side, we would more or less receive these signals to virtual inputs and can then perform the required action. This is relatively straightforward, but it's not very well using the semantic data model of IEC 61850 as we are using GGIO logical nodes. So a little bit more enhanced approach could be to do what I would call the top-down approach. So now we are using not just GGIO, but we would really use the semantic data model that we have built into our 61850 devices and use the system engineering tool to configure. So use basically the IEC 61850 engineering process as we have introduced it in our part 2 of this webinar series. So now we would use the system tool. We would start with the ICD from publisher and subscribers. Typically these protection relays that support both DNP3 or other communications, as well as IEC 61850, they also support an ICD file for 61850. So we can use that as a basis to create now our signal flow using the standard 61850 engineering process, and then based on that, build our GOOSE messages with the related data sets from the signal flow. So if you look now at the use cases, we would have our protection, in this example, distance elements. We have the key element, which is our trip conditioning logical node, so the trip logic that will go on the device that is the protection device to the breaker interface to trip the local breaker. But the signal will also go to the breaker failure logical node, where we implement the breaker failure functionality. So we verify if the breaker did open. If it didn't open, we may do a retrip, and if it still doesn't work, we have to do what we call the external operate or the external trip. So we have to send now that signal, and that signal will be sent as a GOOSE message to all the devices that are interfacing to the neighbor breakers, and it's typically going to the logic node XCBR there as the interface logical node, and then we will trip the breaker. So that's more or less the application, how it will look in a 61850 model. As a result, we will then now have the GOOSE messages that publish these signals like ptrc.trip or rbfr.opx, publish these signals over our communication network. They may be received by the BCUs, bay control units that interface to the other breakers. So that's the principle of that use case, where we can have DNP3 and IEC 61850 coexisting. Now let's do a little example followed by a demo later on. So for our example, we are using one IED per feeder, which combines basically protection and control functionality. So in case of a breaker failure, an external trip is sent to the other feeders using GOOSE. The device that we are using in this case will be an SCL 401 merging unit and control device with an integrated breaker failure and backup protection function. This device supports both IEC 61850 as well as DNP3. And if we look into the data model of the device, that's the ICD file that we can get from that device. So we see here we have a couple of protection functions, the backup protection. We also have the trip logical node, and the key element that we are using for this application is the breaker failure function, or the logical node implementing the breaker failure function, RBRF, where we have the start object indicating that the function started. We have an opt-in, which would be a local retrip, but the data that has to be sent over the GOOSE message would be the OpX. And in particular, in our example, the general, we are not doing in the example single phase breaker operation, so we just need to send the general trip. This would be then sent to the logical nodes XCBR in the other device. So how do we do now the engineering of that? So using the engineering process, as we discussed last time, we would start with a single line diagram. So using the example that I show here is the Helix STS system engineering tool that we have also shown in the last webinar. So we start with the single line diagram, and in this case I have two feeders that we have. So if one breaker here fails, the other breaker needs to be tripped in order to clear the fault. Next, we import our ICD files and we create our IED instances. So down here we see now we imported the ICD file for this cell 401 device, and we created two instances called F1 BCU for feeder 1 bay control unit and F2 BCU. We then have to define the functions, and as we are only using the GOOSE messaging on 61850, the functions that we are defining are limited to what we need for our little use case, which is basically the trip function of the protection, the breaker failure function, and then the breaker interface function in order to receive the operate external from the other device. So very limited data model, but still we have the semantic model defined in IEC 61850. Next, when we follow our engineering process, we have to define the signal flow for our application. And that's quite simple in this case. We have to operate external from the breaker failure function in feeder 1 that we have to send to the breaker interface function in feeder 2. And in a similar way, the operate external from the breaker failure function in feeder 2 needs to go to the breaker interface function in feeder 1. So quite simple, straightforward design. Using the top-down engineering process and tools, the next step is now that we have defined this signal flow. Next step is to generate the GOOSE control block and the associated database. The Helix tool basically allows us to do that automatically with various options that we can set. And at the end, what we get is our GOOSE control block. So we see in the logic device, in the device F1 BCU, logic device for configuration, we have a GOOSE control block, which this name and this GOOSE control block is sent to the F2 BCU. In a similar way, we have in the F2 BCU the GOOSE control block that is sent to the F1 BCU. It contains the breaker failure op-X signal. Here we see an extract that shows our GOOSE matrix. So we see that GOOSE message is subscribed by the F2 BCU, and this GOOSE message from the F2 BCU is subscribed by the F1 BCU. Okay, now that we have made the design, we can load that design in our tools, and Jackson will show how that is done, and we'll do a simulation of that basically. Best.
All right, thank you, Christoph. So what you see up on my screen now is Distributed Test Manager, or DTM. So DTM is a test and simulation tool applicable to multiple protocols. Today we'll be using it with DNP3 and 61850. So what we saw in Christoph's last couple slides, kind of setting up this demonstration, was the engineering process that you might use to configure the GOOSE communications which went between two devices. So we've taken that SCD, or System Configuration Description file, which Christoph set up using Helix, and we've imported it into our tool, Distributed Test Manager, where I've simulated both of those 61850 devices, seen here on the left. So up here at the top, F1 BCU is a bay controller, which is protecting the QA1 breaker in feeder F1, whereas F2 BCU is a bay control unit protecting QA1 in feeder F2. Now, additionally, I've also set up a DNP3 outstation in this same device, and this is to simulate a device which might have multiple protocols enabled within it. Additionally, I've gone ahead and I've taken my breaker failure signal, which Christoph just described, which will be sent from F1 BCU over to F2 BCU, and set it up so that when this breaker fails, it publishes out that GOOSE message, which is received and will open this breaker should this breaker fail. And additionally, that'll be published out in the form of a DNP message on my DNP outstation that's configured on that same device. So over here in the middle of the screen, you see a one line representing this substation that we've configured. And over here, you see a couple very large buttons, the first of which is my F1 QA1 fault. So when I click this button, it'll simulate a fault being present on this breaker over here on the right, QA1. And if I go ahead and click it, we can see that that breaker does in fact open. Now, if I was to reclose that breaker and reset my simulation, and then click these two little check marks over here, this is going to change it such that this breaker is now disabled. Now, when I click this same button to indicate a fault has occurred, my breaker will no longer be able to open, and that will initiate my breaker failure scheme. As part of that scheme, that RBRF, which is the logical node for a breaker failure, will publish out its op-X general, op-X being operate external, and that general message will be set to true. And because it's configured to be part of a data set that's part of a GOOSE control block, it's going to be sent out across the wire. And this second BCU, which is protecting this breaker, will receive it and open. So let's go ahead and give it a try. As I click the button, you see that this breaker, sure enough, did open. So that's all well and good, but now let's take a look at what it looked like from a protocol standpoint. So first I want to take a look on the 61850 side. So what we see here on the right side of my screen is a data model which corresponds to this F1 BCU device. As I drill down into the logical device protection, I can see my RBRF, and sure enough, I can see that that value has been set to true. And again, just to reiterate, if I come up here to my GOOSE control block section, in my LN0, I can see that GOOSE control block has been configured. I can locate the data set for it, and I can see the two signals that make up this GOOSE message. And that will be opx.general, which we just discussed, and then the quality is included as well. And we'll take a moment, or in just a moment, we'll take a look at what that looks like on the wire. But before, I first wanted to come over to my DNP device or DNP outstation that I've also configured on the same device. So you'll notice it only has one point. I thought it would be ideal to keep it simple. I've named that point F1 QA1 breaker failure. And sure enough, we see that value is set to on as well. I could reset my simulation and reclose my breaker. We see that it's gone back to false. And as I click OK or click default, it will in fact come back to true. So now, in order to just kind of drive this point home, I want to take a look at a couple of our other tools so we can see this visualized on the wire. To do that, I'll be using first Test Suite Pro. So 61850 Test Suite Pro, which is what you see up on my screen now, is a visualization and testing tool that's specifically used for 61850. You might recognize it from some of our other demonstrations that we've done as part of our other webinars in this series. Specifically, what I want to use today is our GOOSE Viewer module, seen selected down here in the bottom right. And you can see I've got that selected and I've already begun capturing. And as such, I've already captured several GOOSE messages that have come across the wire as I've been triggering that fault. And I can click on one at a time, and then over in the right pane, I see the contents of that GOOSE message. Every time a new GOOSE message is sent with updated values, not necessarily retransmission, but a new one, the state number will increase and it will appear in this list. If I was to hold down the shift and click multiple of these, I can see that the value has changed as I've gone ahead and clicked that button a couple times over in DTM and generated several GOOSE messages. And each of these that I've highlighted and selected appear as separate columns over here on the right. And then what's highlighted in yellow is what's changed from one to the next. My quality, indicated by this Q down here, which is one of the data attributes within this data set, stayed constant throughout, but the OpX or operate external signal from my breaker failure logical node has changed from true to false and back to true. So that's just a way to visualize the GOOSE signal that was sent between these two devices when the breaker failure occurred. And now in a traditional substation, that might have been a wire, but now we've replaced it here with GOOSE. But now for the DNP3 component. So while GOOSE was replacing a wire, we still need to report the fact that this breaker failure occurred back up to SCADA, and that's what we're using our DNP3 for. This might be captured in an alarm on an HMI or locally or passed up through a gateway to a control center. To visualize that, I want to show one more tool, which is Protocol Test Harness. Protocol Test Harness is one of our legacy tools. It's used for creating outstations and masters in a variety of protocols, including DNP3, Modbus, 101, 102, 103, and 104. In addition to a device simulator for those different protocols, it's a very powerful network analyzer tool and can also be used for conformance tests for some of those protocols. So now I want to create a DNP3 master in order to be able to read the values from the outstations that I've just created. In this case, I've just used default settings on both ends, so I can go ahead and hit open. And when I do that, you can see in my protocol analyzer window up here, it's going to do an integrity poll. And so it's going to reach out from my master that I've just created and request all of the data from the master that I've just created to the outstation. And probably most important, I can see that my binary input 0, which is the only data attribute that I have, is in fact set to true. And sure enough, if I come into my data view window within the tool, I can see the master that I've just created, and I can see that my binary input flag is set to on. And with that, we've kind of demonstrated what it would look like to have a multi-protocol device with both 61850 and DNP, and how that could be used in conjunction in a basic way. GOOSE to replace our wires, but still holding on to DNP to pass information up to both our local HMI and SCADA. And with that, I'm going to go ahead and pass it back over to Christoph, who will continue with slides.
Okay, Christoph, you should be presenter.
Yes, thank you. So you should see my screen again. Okay, so the next use case that we are looking at will talk about a second use case, which will be the configuring a gateway using DNP XML file with IEC 61850 mapping. So basically, the situation that we have now is we assume we have an IEC 61850 substation that we created. So the local communication is always IEC 61850. We also have a local HMI, but as the communication to our control center, we are still using DNP3. So our gateway now has to convert from IEC 61850 to DNP3. To perform that, there is an IEEE standard that was developed that is discussing how we best can do that. So the standard that I would like to introduce is IEEE 1850.1, and it is about exchanging information between networks implementing IEC 61850 and IEEE standard 1815, which is the DNP3 protocol. The standard basically addresses two use cases. The first use case where we have a 61850 client in the gateway, so we have locally a 61850 system, but then remotely we have DNP3, so in the gateway we have a DNP3 outstation. The second use case addresses the opposite direction, and it's typically used when we want to integrate in our IEC 61850 substation some DNP3 devices. So in that case, the gateway will be on one side a DNP3 master to communicate to the DNP3 device, and on the other side, it will be an IEC 61850 server to integrate the data from that device into the IEC 61850 system. The standard defines mapping rules to map IEC 61850 data attributes on DNP3 data points. It also defines extension to the DNP3 XML device profile to describe such a mapping, which can be used to configure the gateway, and we will explain how that works. So this slide shows the use case again that we are looking at for our example, which is the case A, where we have a local IEC 61850 system and remotely we are talking DNP3. It's a typical use case that we have in many substations today that are using 61850 locally, but still DNP3 is used as communication to the SCADA control center. So from a configuration perspective, we have on one side the ICD files from the devices that we have to integrate into the IEC 61850 system, but we also have the DNP XML device profile files, which in the early stage describe the capabilities of these links. So basically, what can the master, what can the outstation support with regards to DNP3? One example is typically the indication if they support double bit information or if they only support binary inputs, so single bit, because that has, as an example, an impact on how we would map the position of a breaker onto the DNP3 system. When we have done the engineering, we may have an output file, which is a DNP3 XML device profile that may contain the IEC 61850 mapping, and I will show how this is integrated. And we also may have, or we have of course as well from our design of the local substation, an IEC 61850 SCD file. Also in this file, we can optionally include the DNP3 mapping information. The standard describes, so the IEEE 1815.1 standard describes multiple scenarios, how we do such a design. The scenario that we'll have a closer look at is called scenario A1, And that's basically the scenario where we assume we have a new system, so we can create the point map of our DNP outstation that communicates to the SCADA system. We can create that point map based on the signals we have, so we don't need to map on an existing point map. So the workflow would basically be, we configure and select the 61850 signals that we need to send to the gateway. We can do that by selecting the data, configure reports and data sets as we would have, are sending them to the gateway. And then from these data sets, we can extract the information that we need to send forward. So in the next step, we can create DNP3 point list from the data sets associated to the reports based on mapping rules defined in this standard. We can identify what kind of DNP points we have to create. And then we can create the configuration file, which basically will be the DNP3 XML device profile with mapping information. So in order to better explain and understand how that works, I will go a little bit more in the details of the IEEE 1815.1 standard. So that standard basically defines mapping principles. The mapping depends on the IEC 61850 function constraint. If we have status or measurement information, so the typical operational information that we cannot write, we map this on inputs in DNP on DNP input points, as these data are provided by the process and we cannot really write on them. However, if we have data attributes with the function constraint like set points can be written, so we use DNP output points in that case. The standard also defines some specific rules for certain 61850 data attributes. As an example, enumeration attributes that we have, like the data attribute control model that we use to configure what control model that we are using, like select before operate or direct operate. This is an enumeration, and this is defined to map on DNP3 analog output. The large part of this 1815.1 standard defines mapping tables that are provided to specify mapping on one side of the IEC 61850 common data classes, but also of the what we call the constructed attribute classes that are defined in the part 7.3 of IEC 61850. And I will give you a few examples, extracts from that standard. The first one is the mapping of analog value, which is a constructed attribute in IEC 61850. It contains both an integer representation of the value as well as a floating point representation of the value. This DNP mapping standard defines that in both cases, the preferred, so the first choice of mapping would be to use an analog input of the type floating point in DNP3. And if that is not available, as a second choice, we would use an integer analog input. Depending on what we are using, the mapping rule that are defined is either int to analog input or int to analog input floating point. For the integer value in 61850, where we have in 61850 a float value, the mapping rule is float to analog input or float to analog input floating point. This mapping is applied when we have the analog value in a data attribute that is a measurement. If you have the analog value in a data attribute that is like a configuration attribute or a setting, set point, then we would preferably use analog outputs, as we can, in that case, also write the values. However, IEC 61850 provides the possibility that an IED may have certain configuration attributes predefined and they cannot be changed. As an example, a deadband parameter could be a case where you have a predefined value and it cannot be changed. So in the case if that cannot be changed, which we can see in the ICD file from the device, we also will map it on an analog input. So that's more or less what is defined in this IEEE 1815.1 standard. Now let's have a second mapping. Let's have a look at the second mapping. And I use here the mapping of a common data class. And the common data class we are using is the ACT, protection activated information, which has multiple attributes like general, phase A, B, C, neutral. All those, if present, each of them shall be mapped on an individual binary input, following the rule Boolean to binary input, as those data types in IEC 61850 are all Booleans. We also have quality and timestamp associated in 61850, and DNP3 has as well quality and timestamp elements, so there is some specific mappings defined in DNP for that. Certain information like the description that we have in 61850 are not supported directly by a mapping into the online data model in DNP3, but the DNP device profile supports the possibility to have a description on the data point. So the description here would only be mapped into the device profile, but would not be available as a DNP data point. Okay, now let's have a look on the mapping of quality. And IEC 61850 has a generic definition of quality. However, DNP3 has different variations for binary, control, and analog points. And what I show here is the mapping of quality for binary information. So at 61850, what are relevant for binary information is the validity, where we have basically valid, invalid, or questionable. This maps on the DNP3 flag online. And like in 61850, when validity gets invalid, there may be other attributes in the detailed quality set as well in DNP3. So in 61850, some of our attributes that are what we call in the detailed quality, like oscillatory, old data, we also have a corresponding element in DNP3, which will be the chapter filter or communication lost for those. 61850 also supports the possibility of doing substitution, in which case the source, instead of being processed, would be substituted. In DNP3, that will be reflected with the DNP3 quality local forced and remote forced. Test or operator blocked, which are additional elements in IEC 61850, would also test would be either local forced or remote forced. Operator blocked would map on remote forced. So again, that's the mapping as it is defined in our DNP in this 1815.1 mapping standard. Mapping of timestamp, we basically have, besides the timestamp that we can map into the DNP3 timestamp, IEC 61850 also supports a timestamp quality, a time quality. So the time quality directly is not mapped, not supported by DNP3, but we can map the attributes that we have in the time quality on binary input and analog input data points. So there's also a mapping defined how this can be done. The other attributes of our timestamp, they directly map into the DNP3 time. Preferably, if DNP3 doesn't support time, they can map on two analog input or analog output points. But as I mentioned, the time quality cannot be directly mapped, but the 1815.1 standard also defines a way how we can map them on individual binary inputs and analog inputs. Okay, now that we have seen how the 1815.1 standard is basically built up, we will talk a little bit about the DNP3 XML device profile. DNP standard defines a XML-based way to describe the device profile, which contains multiple sections. In the mapping standard, there is one section added, which is called the IEC 61850 device mapping. And this section, together with the section of the profile that defines all the data point lists, can be used to describe the mapping. The mapping can either be rule-based, based on the rules we have just had a look at, or it can be equation-based, based on equation. As an example, when we have to map a double point on two binary points, we will use an equation-based mapping. But in the most cases, we'll use a rule-based mapping. The slide here is just an example how this mapping is defined. We have one example of a rule-based mapping, where we have the rule, we have a DNP3 path and the 6150 path, and we will look at that in our example later. But here we also have an example of an equation-based mapping, where we basically have an equation that converts some analog values based on scaling. Okay, with that, we will go to a second example and demo. And the example is basically how we map 61850 to DNP3 in a gateway. So in example, we assume we have a substation with IC 61850 that was configured using the standard 61850 engineering process. We have reports and associated data sets that we use to configure the reporting from the devices to the gateway. And from those data sets, we will use a tool that can extract our leaf data attributes. That's where we have the values, and can apply the mapping rules defined in IEEE 1815.1 standard to determine the DNP3 points. And that's what Jackson now will demonstrate.
Okay.
All right, thank you, Christoph. So as Christoph mentioned, I'll be talking about how you can how you can automate the process to map between 61850 and DNP3. But to kind of do that, I want to start out by showing what it means to configure 61850 MMS reports. So to do that, I'll be using SCL Navigator, which is what you see up on my screen now. SCL Navigator, short for System Configuration Language, is a tool that's used to edit and view SCL files. In this case, I'm viewing the SCD file, which we discussed earlier. So this is the same one that I used to create my simulation over in DTM. Last time I talked a little bit about what the different sections are. Today we'll be focusing mostly on the IED section with a little bit of a data template section. Now remember, the IED section is where we define the data models and the capabilities for our individual IEDs, which make up our substation. In this case, we have 3 IEDs configured, the 2 bay controllers that we saw over in DTM, as well as a client configured. Now the data template section down below, let's say that we were to use some of the same data objects or logical nodes between these 2 different IEDs. Instead of needing to define the data models completely in each IED section, we can just reference different logical nodes, and those logical nodes can reference different data objects, and those are defined only once down in the data template section. And that'll come into play here in just a moment. Starting with this top IED that we've configured, I'm going to expand it out, come down into the access points section, look at the server that we have configured on this device, and then look at the top logical device config. Within that, we have our logical node 0, where we can hold much of our configuration information, and specifically this is where our report control blocks are configured. So here you see we have 2 different report control blocks configured, down here, and each of those is associated with a data set defined in this first tag. Now those data sets are linked to just right up here above. And if I expand out those data sets, I can see the data that's actually going to be sent out in the form of the 61850 report. So just to recap, we have 61850 reports enabled on this device. So these are messages or collections of messages that will be sent up to SCADA. And anytime, based on our trigger options, that any of the data contained in one of the data sets associated with this report, anytime it changes, we're going to send out that associated message. So now here we see, as I mentioned, the different data objects that make up this data set, but data objects aren't really where the story ends. So data objects are just containers, much like logical nodes, it's just one step lower. And data objects contain different data attributes. Data attributes are really what correspond to individual points in DNP3. So in order to know what data attributes are going to be included in this report, I first need to look at the DO or data object that's included and look at the functional constraint that's associated with it. And then if I right click and locate, navigate to data, okay, so this is a definition for the RBRF. That OpX that we are looking at that was part of our report data set was in the RBRF logical node or in an instance of it. And then this OpX is type ACT. So if I want to know what data attributes actually are contained within OpX, I can right click and navigate to my template for this specific data object. And as I expand this out, I can see the actual data attributes that'll come across the wire when this MMS or 61850 report is published. And the point that I really want to drive home here is these are the leaves at the end of the tree. This is kind of where it ends. And this is what maybe most directly corresponds to an individual DNP3 point, whereas the data object is just a container which holds multiple of these, in this case, 1, 2, 3, 4. The data attribute is a single point in my DNP map to relate the two. So now I've created my MMS reports. So this is what's going to be published by my devices and going to be received by my gateway. But now I want to configure my gateway with what DNP3 points are going to be coming out of it. In this case, we do have a tool here in SEL Navigator in this build that allows me to create that DNP3 point map. So what it's going to do when I click this button, it's going to go in and look at the reports that I've generated across all of the devices in this SCD file. It's going to look down into the data sets of those reports, and then based on the data attributes that contain that data set, so for example, this opx.general data attribute that I see here will correspond to this opx.general that's here at the top of my DNP mapping list. And it's going to do that for each and every data attribute in each and every data object that I have within my data sets of my different report control blocks. Now when I click generate CSV file, I've already done this and saved it out, and we can take a peek at what that's going to look like. So this is a template for this DNP3 data map that our gateway is going to be outputting on the other end. Names and descriptions are something that Christoph is going to be going into a little bit more detail later, but I do want to draw our attention to point type and index. So point type, as I mentioned, this OpX general is a binary value or a Boolean in 61850 parlance, and that corresponds to a binary input in DNP3. In the DNP3 standard, 1 is used to indicate that data type, binary input. Whereas this position value for my XCBR position in 61850 is a double bit indicating 4 possible states, open, closed, intermediate, and unknown. And that corresponds to a double bit in DNP3, which we define with point type 3 in the standard. And then finally down here at the bottom, we have some analog values, our 3-phase voltages and currents. And those are going to correspond to analog inputs, which are defined by the number 30 in DNP3. And then lastly, what the tool did for me was create these indexes. It really just does this automatically. You could come in and edit them should you choose, but it basically starts, well, I've got 3 different binary inputs. I need to start at index 0, and there's just increment from there. Once I switch to a new data type, in this case 3, we said corresponds to double bit. Again, we start at 0 and increment, so on and so forth. Now, in this case, we've exported this as a CSV, which I'll be using a little bit later to give you a preview in DTM, but we could imagine a future where you would also export this into a DNP XML device profile, should your gateway support that as an input. And to give us a little bit more insight into what that DNP XML device profile that contains that mapping looks like, I'm going to turn it back over to Christoph, who's going to explain that a little bit more. Christoph, back over to you.
Yep, thank you, Jackson. And I will share my screen again. So in order to have an easier view, I created here a screenshot that summarizes what we have seen. So basically, as we mentioned, the DNP XML file will define all the DNP points. An example, the binary input points. It will define each binary input there with an index, and we can give name and description. The key is also that we have the change event class. In our mapping section in that same file, we have now for this data point that we have just looked at, the operate X, we have the mapping rule. So we have a rule-based mapping that we are using here. The rule is from the standard, which is called Boolean to binary input. And what we see, we have the path of the DNP data, which refers down to the data point list in the same DNP XML profile file. It goes down the hierarchy to the input point with the index 0, but then it goes also to the data, and it's the element state of that input point that we are mapping. The same way we have the IEC 61850 path. This points now into the IED, ICD, into the SCD file, and it basically points to the device F1 BCU logical device Pro. What we see here, the logical node breaker failure RBRF, the prefix BFR1 RBRF, the data object OpX, and the data attribute general. And we also indicate the common data class, because that's what we are using for the mapping, the data type of this, and the function constraint. So with that, we have completely defined the mapping between our 61850 world and the DNP world that we are sending on the other side of the gateway. And before we go to the next use case, I would hand over to Beth for a first series of questions.
Thanks, Christoph. Yes, we have had several questions come in that I see are being answered online. I will pull a couple of them, and we are running a little bit tight on time, but I will try to get at least 2 questions in here. The first one, this is for either Christoph or Jackson, whichever one wants to take it. We have a controller which does not support DNP3, but supports IEC 61850. Is it possible to support an external DNP master or outstation to integrate to our controller which supports 61850?
Yes, I mean, I think that ties in really well with Christoph's last point. So I think you would want to use a gateway or maybe just a protocol converter, and those two really overlap in this case. But yeah, you would want to have some device such as our gateway, SCADA data gateway, which could convert between DNP3 and translate that over to 61850. And you could leverage the 61850 engineering process as just discussed in order to make that configuration a little bit easier. SCADA data gateway, our solution for that exact problem, is a software-based solution. So you would install that on a Linux or Windows PC.
Okay. Thanks, Jackson. Like I said, we are running a little bit short on time. We only have about 8 minutes left in the webinar, so the questions are continued to be answered by the engineers online, so please continue to submit them, but I'd like to switch back to Christoph so we can make sure we get through all the material.
Okay, thank you, Beth. So yes, now we will have together a look at the last use case, which is basically using the 61850 engineering process by combining IEC 61850 and DNP3. So the use case is a little variation of what we just discussed in the gateway. Now we would assume we are still using DNP3 in the substation to communicate to our gateway, but we also have 61850 support. So our device is multi-protocol support. It supports also IEC 61850 for the communication to a local HMI. The basic idea of the approach now is that we use, of course, the 61850 engineering process to configure the 61850 aspects of the substation, but we use that process as well to configure the signal flow to the gateway, even that this will be used DNP3. The reason we can do that is because typically model includes mapping to device internal variables, and we'll show how we use that. So basically, using the same approach that we discussed for the configuration of the gateway, we can determine the DNP3 points that we use for the communication to the gateway based on our signal flow that we have configured in 61850. So the workflow is summarized here, but I think it will get a little bit more clear when we then just go through the example. So we would import our ICD files for the IEDs in the 61850 world. And as I mentioned, this device that support both IEC 62050 and DNP3, they also have an ICD file. We would then configure the signals that we send both to the HMI and gateway using 62050 signals, but having in mind that the ones to the gateway, we will use DNP3 points. From the data sets, we will, as it has been shown before for the gateway mapping, we can now extract the information that we need to create as DNP3 points. And instead of using that extract for the mapping, we use it now to define the flexible point map from the DNP device. So we create now the configuration file for the device, which can be a DNP XML device profile, but it can also be a vendor-specific file. So how does it look? So basically, the ICD that we are using, the cell F401, the ICD file of that device we have seen before already. We have, as an example, our breaker failure logical node, the signal OpX with the attribute general, but what this ICD file contains as well is a reference to the internal variable. So for all of the data that this device supports, we have reference for the internal variables. So when we extract the data points that we need to send to the gateway, we can also extract the internal variable that this corresponds. So from an engineering process, we now define our data model, the full data model, not just what we used initially for the GOOSE, and we can configure with a tool. We basically can select with our system configuration tool, the Helix STS, we can select the data points that we want to send to the SCADA gateway or that we want to say to the local HMI. And based on that, we can configure our reports with the corresponding data sets with all the data members. Now we can use the same tool that Jackson has shown before to extract the data that has to be sent to the gateway. So we can extract and create out of that a DNP3 point list. As we have as well the internal variable name available, we can also include that variable name in our DNP mapping point list. And depending on the device, you can now use that to configure your DNP point list, the points that will be sent to the gateway. In our example device, the device accepts a file that basically introduces the points and links them to the internal variable that we found based on our ICD file. So with that, we can use this IEC 62050 engineering process, extract the information that we need to send over the DNP link to the gateway and configure this DNP points in the device. And Jackson will demonstrate how this will then look.
Okay, Jackson, you should have the screen.
All right. All right, thank you, Christoph, and thank you, Beth. So just to briefly recap, we're back over here in SCL Navigator where we've set up our data sets. And now instead of just creating a CSV file that we want to use to configure our gateway, we want to create a CSV file that we can load directly into our device to configure our multi-protocol device. And this is in a situation where we might be sending, as Christoph described, MMS out to our local HMI, but DNP up to a gateway, for example, for our offsite control center. So just to reiterate, once I have my MMS reports configured or my 61850 reports configured in my data set, I came up here and I created my DNP point map, and that gave me this CSV file. Now, using the proprietary format, in this case, we have it configured for DTM, but you could, with small changes, have this be set to, for example, the SEL format that would allow you to configure their DNP outstation. In any case, once you have this CSV file, we're going to come back over to DTM, or Distributed Test Manager, where we started the day. Now, remember, I have the same two sets of devices, or IEDs, and one of them has a DNP outstation on it. This is my multi-protocol device. So now I can edit the database, the DNP3 database, on this DNP3 outstation. And instead of having just a single point that I had earlier, I'm going to import the CSV that I output as a result of the engineering process using SCL Navigator. Now, when I hit OK here, you can see that it's gone ahead and created all these points. Just going to hit OK one more time, and then we'll see that it does import all of my tags right here into DTM on my DNP3 outstation. So this is really applicable in a case where you have a configurable DNP map on your outstation. So now, just like we did before, I could do the same test where I trigger a fault on feeder 1, and it's going to open my breaker on feeder 2. But now we see I have more points configured in my map. My operate external, my operate input, and my start all have changed to true. And then the same thing over on my 61850 server. Before we looked at GOOSE control blocks, but now I also have reports configured on this device as well. And we'll see if we look at the data set for this report that we've got that same information available. So now to kind of bring it all back together, I could look over in Test Suite Pro to see this report being published. And to do that, I'm gonna just drag Test Suite Pro back over onto the screen, and you can see several different reports have come in. So remember those 3 values that changed in DNP? That was the start, the operate, and the OpEx. Because those changed at 3 different times, we actually generated 3 different reports. If I was to do a reset, for example, I'm just going to click that real quick. We'll see that I generate one more report that comes in that does contain all 3 data attributes, and that's because they're all 3 reset at the same time. And again, this is just showing in my report viewer over in Test Suite Pro, the SCADA messages that will be sent out to your local HMI. In order to see the DNP3 messages that would be sent up to maybe my gateway or my remote control center, I'm going to go back over to the tool that we looked at earlier, which was Protocol Test Harness. And I'm going to create a SCADA master again, using the same process as before. Just open DNP3 master. I can use the default settings in this case. And when I do it, it does do that same integrity poll. But in this case, instead of seeing a single binary input like we had before, we see that we've retrieved all messages that exist on this, all signals or points that exist on this DNP3 outstation. And if I come back over to my data view, I can see that a little bit more clearly in the form of what those values are currently at. Now, if I do want to incorporate the names that I've set up as a part of my engineering process, I can do that as well. By default, DNP3 can discover the data points that are on your external device, but not the names. But if I want to apply that same file, the CSV file that I set up before, I can just do that here. And we'll see that now the descriptions have updated to include those that I defined as a part of my engineering process. So now I've kind of been able to leverage that process, which we traditionally think of being associated with 61850 communications, and apply just the whole 61850 engineering process to define my DNP3 data map and apply that not just to my device or my outstation, but also to my master as well. So with that, we are kind of coming to the end and running out of time. So I do want to just wrap it up with a couple conclusions before I turn it back over to Beth for some Q&A. So bear with me for just a moment as I pull up my conclusion slide. Okay, so I hope that we've been able to demonstrate today that both DNP3 and IEC 61850 can and should coexist, and there are many reasonable use cases to have both in the same substation. That we've shown that 61850 can be introduced stepwise. You can start out with GOOSE and kind of work your way up to have a full 61850 system. And you don't need to redesign your whole system to introduce individual pieces. For example, replacing wires with GOOSE. And then finally, I hope that we've demonstrated that applying the 61850 engineering process to DNP devices introduces a machine readable format in the form of the SCD file and then the different proprietary CSVs or DNP XML device profiles that you generate from that. And that automating these steps allows for tools to better visualize your design. Thank you so much for attending. Please stick around for questions. And with that, I'll turn it back over to Beth.
Thanks, Jackson. Yeah, so we are a couple of minutes over. I appreciate everyone hanging on the line a little bit longer. I do have a couple of final thoughts on the webinar I'd like to review real quick before I switch into questions. When you sign up for the webinar today, you will be presented with a survey. It only takes about 2 minutes. We are always looking for your feedback, so I really appreciate it if you take the time to fill that out. The recording for this webinar will be posted on our homepage in a couple of days, so you can get it that way. If you fill out the survey, you will also get a follow-up that will include a link to the recording, as well as this, the presentation will be attached. You can also go to our website and sign up for our email newsletter, which will keep you notified about future webinars, training events, any product releases. The sign-up form that you see on the right-hand side of the slide is what you'll see on our website. So please, if you're not already signed up with that today, go ahead and get on that email newsletter list. And I also want to mention that any of the tools that you've seen here today, in addition to the SCADA Data Gateway, which came up through the questions, you can go and download an evaluation license and try out the tool at any time from our website. So if you go to the website and you set up an account and log in, you'll get a 3-week evaluation license. Again, that'll be for our tools and for our gateway. Specific to the gateway, a couple questions came up about a proof of concept. We can provide longer term evaluation licenses for that to support your proof of concept. So please just email sales@trianglemicroworks.com at any time if you need a longer term eval license. So with that, we still got a number of folks online. I will switch back over to questions. We've had actually this one is for you, Christoph. I'm using IEC 6870-5-104. Is there a similar standard using to 1815.1 for the mapping?
Thanks, Beth, for the question. Yes, there is. So, like we have the IEEE standard for the mapping of 6150 on DNP3, there is within the IEC 6150 series the technical specification IEC 6150-80-1, which addresses the mapping between 61850 and 875.101.104 protocol in a similar way.
Okay. This is more of an opinion question, really, for both either Christoph or Jackson. Is it common to use gateways to translate between 62050 and DNP3?
Yeah.
Yes, I think, as I mentioned, when we
I think it's very common. It's common to use MMS in your substation. Please elaborate. But sorry, go ahead.
You're breaking up a little bit, Jackson.
Christoph.
Okay. So yeah, it's very common. Typically, when we have existing systems, you have the DNP3 communication to the substations, or maybe 875.101. So when you introduce IEC 62050 in your substation, that does not mean that you change now as well the SCADA communication up to your control center. So applying there 61850 is applying there a mapping, a gateway that maps between the traditional SCADA protocols and the IEC 62050 is very common.
Okay. Next question, Christoph, this is for you, is specific to 62050. I believe, what would happen to a network when there are 2 IED devices with the same IED name?
That would not be a very good idea, because the standard requires that the IED names are unique on the network, because the IED name is part of the address that we use to identify the data. So the IED needs to be unique, and typically you have naming schemes how to create these names for the IEDs so that they remain unique.
Okay, well, I believe that wraps up all our questions. Everything else has been answered online. So again, I just want to thank everyone for attending and for staying on with us a little bit longer than scheduled. Please fill out the survey and we will follow up with additional information. So thank you, everyone.